Hey everybody, I'm just checking in for the this how to code virtual office hours. I hope everybody's doing well. Here in Canada, this is a holiday, so we're having a long weekend. But in other places, people may have a work day today. Anyways, let me just jump right into the questions. We got one this week, and let me do the screen sharing here. Here we go. It has to do with abstract fold functions, and in particular this problem here. And since this is the only question we got this week, I thought I'd go ahead and work it in some detail. So let's go over here to Dr. Racket. And here's the starter file for this problem. You're given a set of data definitions for mutually recursive types. It's mutually recursive because dir refers to list of dir, and list of dir refers both to itself in a natural recursion, and it refers to both itself in a self-reference, and also refers back to dir in a mutual reference. So dir and list of dir are tied in a mutual reference cycle. Dir also has a reference off to image, which has a self-reference but doesn't come back. So dir and list of dir are in mutual reference, and there's this attached type list of image. And the first thing to do is design an abstract fold function for dir. So let's see, there's the type comments. What I'll do is I'll just copy, well, I'll scroll back and forth. I'll make the font a little smaller. Right now I have the font sent to the size I use in lecture at UBC, and that's a little bit too big for working in this setting. Let's do that. Okay, so here we go. Let's see, there's three types: dir, list of dir, and list of image. So if we package all of that up, we're going to have a local with three definitions in it. Let's see. There'll be a fun for dir. I'm just doing the template rules now. Fun for dir d. And let's see, that's a compound, so we do the selectors, dot, dot, dot. Dir, I'm having a hard time with my typing today. Dir name d. I'm having a very hard time with my typing today. Dir name d. Dir sub dirs d. Dir images d. And let's see, this is a reference, so fun for dir goes, for fun for LOD goes there. Hang on just a second. I just got to pause for just a second. Should always take the key to the room. I know, because that's what's the answer you want. Hang on, I'm back. Had to let the dog out. And let's see, dir images is a list of image, so fun for LOI there. And then let's see, define fun for LOD. LOD, this is the usual thing, const empty LOD. Something else first LOD. oops, sorry, hang on. First LOD, rest LOD. This is a reference back. This is the backlink of the mutual reference, fun for dir. This is a self-reference, fun for LOD. And then we got fun for LOI here. Since I'm typing so badly today, I'm just going to copy this one rather than type it all from scratch and just update it. So this will be LOI, I. There's no reference here because images are a primitive type. And then the trampoline calls the for dir of D. Sometimes it's nice to put a blank line there so you see the trampoline a bit better. Okay, let's quickly do the signature. Oh, we first have to turn it into an abstract function. So every set of dots gets a parameter. So I like to call the functions C for combination. And I like to call the base positions B for base position. Fix the indentation with Command I, and let's put them all in. C1, C2, C3, B1, B2. Now let's do the signature. Let's see, it consumes 3 functions. In 2 bases, and it produces some, and it consumes also dir. B is definitely a dir, so we'll say that. And it produces something. Okay, let's do this. Let's say that this function is definitely going to produce x, and let's say that this function, now anyways, is definitely going to produce y, and this function, for now anyways, is definitely going to produce z. Okay, well, we know right away the trampoline calls fun for dir. So the whole outer function produces whatever fun for dir produces. So this whole thing produces x. Let's look at C1. Let's see, C1 consumes, well, the first thing it consumes is a string because dir name is a string right there. So C1 gets a string. It gets the result of fun for LOD, which is a y. And it gets the result of fun for LOI, which is a z. And we've already decided that it produces an x. Okay, let's look at fun for LOD. Fun for LOD better have a fold-like signature, right? Because it's a fold-like thing. Let's see, excuse me, take it back. That's fun for LOD, but I'm right now working on C2. Let's see, C2 consumes the result of fun for dir, which is an x. It consumes the result of fun for LOD itself, which is a y, and it produces a y. So that thing right there has a signature like the argument to fold R. Okay, that has a signature like the function argument to fold R. And let's see, B1 had better be a y because it's in base position for fun for LOD. So that's a y there. And fun for LOI, let's see, C3 is going to take an image, because the first of the list of images is an image. It's going to take the result of fun for LOI itself, which is a z, and it better produce a Z. And let's see, B2 had better also be a Z. Abstract fold function for dir. And we can say that we templated it from the types. You know, as soon as you've said abstract fold function, you've kind of essentially said that you've templated it from the types. Well, we could just go ahead and say it. Okay, so one of the questions that was asked has to do with how you test one of these things. And you know, the first test that I like to use is the copy test. I'm gonna hand it some big thing, like let's say D6. And I'm gonna hand it some other arguments in here, a bunch of them. And the question is, do I get back D6? And the copy test is good because it really tests all the positions. Okay. The thing to remember is, how did we get here? This was ... and then the selectors, right? So if you put the constructor there, because this was the compound rule, if you give it the constructor at C1, then you're putting the compound back together. Let's look at this. This was also a compound rule. This was a cons that we're taking apart into first and rest. So if we put cons in for C2, then we'll be putting this cons back together. And the same with C3. This was a compound rule, the selector first and rest. So we'll put it back together with cons. This is the base position of the self-reference that's constructing the list. So we'll put empty because that's the base position of a list. And here we'll put empty as well. Right there, if all goes well, we ought to have a simple test. And that test is actually quite complete because it's testing that each of these positions is used properly. Once you have that insight, you can think of other things that you want to do. So for example, you could collect up all the directory names, or you could collect up all the images. But notice as soon as I do that, I'm just using one position or another. So it's not as complete test as this. But let's go ahead and collect up all the directory names. I'm doing that because I know I'm going to need some special functions. Folder. What's C1 going to be? C1 has to be a function that keeps this name and keeps any names that come out of here, but ignores the images because there are no images. So let's define that. That's a weird function. Define C1. It's going to take a name. It's going to take a list of names. And then it's going to take some result of the recursion on the list of images. We call that the recursion on list of dirs. And it's just going to cons the name onto the result of the recursion on list of dirs and ignore the RLOI entirely. That's C1. Let's see, what does C2 have to do? Well, this is going to produce some list of names, and this is going to produce some list of names. So C2 is just append. And C3 can be anything it wants. At the end of the day, you know, we can build a list, we can not build a list. We're going to ignore whatever comes out of here. So, you know, if I want to not take the trouble to make a list, I'm going to ignore. I can say I result of the recursion on list on LOI and just produce back, empty or false or whatever. It doesn't matter what I produce here because I'm going to ignore it. So I'll put in C3 and I'll put in empty there and false here because the result of B2 is also ignored. Oops. And now let's better go figure out what the actual right answer is. Let's see, D3 is D4 and D5. And D4 is I1 and I2. I'm just going to grab this all up here quick. Oh, no, I can see both of them. Let's see, the thing starts out with D6. And then it has a child D4. Because D4 is there. And D4 has I1 and I2. And then we come all the way back to D5, which has I3. Whoops, what argument did I not give it? 1, 2, 3. 1, 2. Oh, I didn't give it an actual. I didn't give it an actual directory to work on. D6, D4, D5. What happened here? Okay, let's look at this. This did one recursion to D4 and D5, but then it didn't recurse again out of D4 and D5. So let's see what's happening there. Fun4Dur calls Fun4LOD. Fun4LOD is there. Fun4LOD calls back to Fun4Dur, so it looks like this is doing it. Hang on a second. Debugging is fun. Okay, I'm going to take this little thing here. And try it with some smaller examples. Oh, it's my mistake. These are images, not subdirectories. This tree is only one level deep, actually. This is a bad example. This tree isn't 2 level deep. So I'm actually reading the test wrong. There are no eyes in it at all because eyes are images, not directories. So this was a case of a bad test, not a bad function. really this starter should have an example in it that's too deep, right? There really ought to be some other directory in here. Okay. So it's always good to have a copy test, and then you can make another test if you want. And I think I've answered at this point all the questions. Oh, also wants to look at part B and part C. So let's look at part B. Design a function that consumes a dir and produces the number of images. Use the full dir abstract function. That's kind of like this. Okay. We could just do a check expect for that, actually, and it'll be essentially the same. And then I'll let you produce the entire function later. Let's see. What we're going to do here is we're summing the number of images. So if we do D6, we want to get 3. Let's see. In order to sum images, the dir name doesn't count. The LOD doesn't count. Oh, it does because there's images in there. So this one and this one both count. So here, what this function is going to do is it's going to take n RLOD and RLOI, but it's going to ignore n and add the other two together. Right? Because if we were editing the abstract function, which we're not allowed to do, but if we were, we would put a plus there and we would delete that. So C1 adds the result of the two recursions. What does C2 have to do? Well, C2 is now just plus. B1 is now just 0. C3 is, what does C3 have to do? Well, it doesn't add the image, but it adds 1 for the image. So this is going to be plus 1, and then the result of counting the rest of the images. These two comments go away. And the base for the LOI recursion is now 0. It really helps to think about the C's as combination positions and the B's as base positions. And so this C combines together the name and the result of the two recursions. And this C combines together the mutual recursion and the natural recursion. And this C combines together the image and the result of the natural recursion. And if you think about, well, how do I combine all those things? Then you say, well, for this position, I ignore the name and I sum the results of the two recursions. For this position, I just sum the results of the recursion, so I just put plus right there. I didn't bother giving it a name. And for this position, I ignore the image, but I sum together, but I add 1 to the result of the natural recursion. Suppose you wanted to add up the sizes of all the images. In that case, this would be plus image area I1, image area I2, image area I3. Well, all that changed there is instead of counting each image for 1, each image has to contribute its area. Well, image area doesn't exist, but we can fix that. I'll just define it quickly here. Image to integer, produce area of image. Define area I 0, expect area, make rectangle 10, 20, solid, blue, fine. Hope it should be 20 so that we fix that bug. Say, what we have available to us is the image width of I and the image height of I. And that's the template, and now we multiply them. Oops, I called this image area. There. Cases. You can now design the actual function that produces the number of images in the directory and its subdirectories. Okay? Because it's basically, these are the functions you're going to pass to it. Let's talk about consumes a dir string and looks in dir and all subdirectories for a directory with the given name. If it finds such a subdirectory, it should produce true. If not, it should produce false. All right. Dir string, and it's either going to produce, a Boolean. Produce true if dir has given name, or if, how about let's say if any dir in the tree and let's see, it's going to take a directory and a name, and that's the stub right there. And let's do some examples. Check expect has dir named. D6, that checks the root. That checks the first of the children. That checks the rest of the children. And this checks something you can't find. All right. Let's set this up. Template as call to folder. Local some stuff. Folder with the last argument being the dir. Let's see, C1 is the combination position for the actual dir. That's what gets the name. So let's see. Define C1, name the result of the recursion on LOD and the result of the recursion on LOI. Well, let's see, if the name is the name we're looking for, I'm going to call this name here N0. If string equal question mark, name of this directory is the name we're looking for, then true. Otherwise, the images, we know the directory we're looking for isn't in a list of images because it's a directory, not an image. So otherwise, let's produce whatever we found in the list of subdirectories. So that's C1. LOD is the combination here. Okay, so let's see. If you're looking at an empty list, you can't find it. So B1 is false. Let me put some spaces in so I don't get confused. That's C2, that's C3, that's B1, that's B2. B1 is false. If you can't find what you're looking for in an you can't find what you're looking for in an empty list. So B1 is definitely false. And what's B2? What's C2 rather? Well, it might be in there. That might produce true or false. And that might produce true or false. So it's really an OR of those two. So I'm going to put OR here, but that OR is not going to end up working. We'll come back to it. And now for C3 this time, look. We already decided that the result of the LOI is going to be ignored. So I really can put anything I want here. This time I'm not going to work as hard. I'm just going to put cons and empty. That's going to build up a list of images which I will ignore. So in the first example, I showed you how to work hard and not do that. But let's just do this for now. Oh, look at that. At least I was consistent about that mistake. Ah, look at this error message. OR is not a function. Remember, OR is not a function. OR evaluates like if and cond. OR is a conditional expression. It only evaluates its second operand if the first operand produces false. So if I want to hand off something like a function, then I got to do something like this. Define C2, the result of the recursion on the dir, and the result of the recursion on the LOD. This is the result of the mutual recursion there, and the result of the natural recursion there. So the result of the mutual recursion here and the result of the natural recursion here. And I'm going to OR them together here. Oh, and I got to put C2 there. Now it works. Problem D is fold OR really the best way to code the function from part 2? Why or why not? Well, the answer here is that the answer here was the OR. Right? Just to be a bit more clear about it, let me code this with if. If that produces true, then true. Otherwise, produce whatever that produced. That's the same as OR. And here you see the problem. If I'm editing the templates, and I put an if there, and I put an if there, then the great thing about this is as soon as I find the thing I'm looking for, I stop. But a fold function doesn't have an if there or an if there. A fold function has a function call there and a function call there, and a function call there for that matter. So the thing about a fold function is the fold function always traverses the complete tree every single time. What C2 and C1 here are doing is they're telling it which result to use. That's what those two ifs are doing, is they're saying which result to use. They're combining the results together, but the fold function is still traversing the entire tree. C1 and C2 can't stop it from doing that. So the answer is that fold_dir is not a very good way to code a search, because a fold function searches the whole tree every time. And usually in a search, you want to quit as soon as you find what you're looking for. Okay, that's all the questions we got for this week. I went through that one in great detail. We know that people are working through course material, and we'll be happy to answer more questions. So just post more questions, and in a couple weeks, I'll answer all of them. Talk to you later. Bye.